Well, I'll begin with a word of prayer. I was looking for my mic. That's not a good sign. It's on me. Anyway. Dear Father, we thank you for this day again. I thank you for the students. Just ask you to just bless our work today. Help us to understand a little bit more about calculus together, Lord. In your name I pray, Lord Jesus. Amen. So, last time we did some somewhat picky arguments to develop Fermat's theorem, Rolle's theorem, and the mean value theorem, right? So what did Fermat's theorem say? Do you guys remember? So Fermat's theorem said says that if f has a critical point where f prime of c exists, then f prime of c is equal to 0. So in short, Fermat's theorem says that if you're looking for critical points, then looking for where a derivative is 0 is a good idea, right? So if you think about this, there are two possible things that could happen for a critical point. What are they? The derivative could exist, right? And then Fermat's theorem tells us that, hey, the derivative is 0 at such a point. What's the other thing? If it doesn't exist, it doesn't exist, right? I mean, it either exists or it doesn't. So if it doesn't exist, that's the other kind of critical point. So that's the other potential place a function could have a local extrema. Either a place where the derivative doesn't exist, or a place where the derivative is 0. So as we're thinking about maximizing functions and graphing functions and so forth, finding all the critical points is really interesting because that tells us all the places where the function can be minimized or maximized, at least locally. Now the question of is it minimized or maximized globally is always a stickier question that ultimately it's not quite answered by calculus. It kind of depends on the overall details of the problem, or what you might call the global topology of the problem. But anyway, there we go. What did Rolle's theorem say? So Rolle's theorem, that's my marker. Rolle's theorem said that if f is function with, we need three things. Number one, f of a equals to f of b. Number two, f continuous on the closed interval from a to b. And number three, f differentiable on the open interval from a to b, then what? There exists c in the open interval from a to b such that what? F prime of c equals to 0. That was Rolle's theorem. Rolle's theorem really just a special case of the more important theorem, which is the mean value theorem, which I usually refer to simply as MVT, most valuable theorem. Not really, just joking, but so if f is function with one f continuous on the closed interval from a to b, and number two, f differentiable on the open interval from a to b, then there exists c in the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. So these three theorems you really need to know for this class. I expect that you know what they are when I talk about them. But of course, like, the mean value theorem is the most important one for you to memorize for your future reference. It's something we use from time to time in calculus. If you want to remember it succinctly, all the mean value theorem says is that for a function which is continuous and differentiable on a closed interval and the open interval respectively, then there exists a point such that the average rate of change is equal to the instantaneous rate of change over that interval. That's what it says. Now, all right, so that's just a quick review of yesterday. I will go on now. So, definition, I guess I'll do it here. F is increasing, right, on U, which is a subset of the reals, if A comma B in U with A less than B implies F of A less than or equal to F of B. And let me be picky here. Check my notes right quick. Make sure I haven't missed an inequality there. I think we're fine. Now, if instead of increasing, you wanted like strictly increasing, on U, then that would give you F of A is less than F of B instead. So strictly increasing would mean that it's, if you have A is less than B, it implies F of A is less than F of B, but increasing allows the possibility of equality. F is decreasing on U, which is a subset of the reals. If A and B in U with A less than B implies F of A is greater than or equal to F of B. All right? And you might guess, what do you think strictly decreasing means? What do you say, F of A is what? Oh, you said F of B is less than F of A? I'm going to say F of A is greater than F of B, but I see what you're saying. I mean, you got choices. We can always take any less than statement and turn it into a greater than statement, but yeah.
Are these definitions related to the theorems, or are they separate?
These are separate. We're starting a new discussion. Yeah. The theorems are from yesterday. So what I'm getting into now is the discussion of what does it mean for a function to be decreasing and increasing, right? And maybe no one ever really carefully defined this for you before, right? Like if I'm teaching pre-calculus, I don't give this careful definition for increasing and decreasing, right? I just tell people stuff like, well, you graph it, right? And wherever it's increasing, and wherever it's decreasing, it's decreasing, right? So if you like, you could, like this, it's increasing there, and then it's decreasing over here, right? And then it's increasing here, right? And so forth, So the graph I just drew, y equals f of x. This example, I guess this is example 1, I suppose. If you look at this graphical example, you guys can probably tell me where is this increasing and decreasing. See, so the deal is, if I have any subset here, oh man, look at that. Is there anything left to do with this marker? I was robbed. Let's see here. So if it was like this, right? If this was a picture of my subset U, see if you look at any two A and B in here, right? If this is A and this is B, then what do you have? F of A is like here, right? F of B is like there, right? And as you can see, F of A is less than f of b, because the function's increasing in the blue, right? And it's decreasing in that red spot, right? So if we just say f is increasing, what does that mean? If f increases on the domain of f, then f is increasing everywhere, right? And if it decreases on the domain of f, then f is decreasing. But we don't usually talk about this concept too much. But in principle, you could talk about a function which is everywhere increasing or everywhere decreasing, all right? But to be careful, the definition of increasing and decreasing, it's a concept which depends on a set, all right? So, simple theorem, if f is differentiable and increasing on u, then f prime of x is greater than 0 for all x in u. And if f is differentiable and decreasing on u, then f prime of x is less than 0 for all x in u. Now this theorem is not quite true yet, which means that that's a problem, isn't it? So let me explain to you why this is true. Why is it true? And we'll discover how the statement of the theorem needs to be modified as we look at the proof. It's not much of a modification. You can write it out as it's stated. Fixing it will be just a simple slash, 2 slashes actually. Okay, so feels hot in here today. Let's see. Yeah, so let's let A and B be elements of U with A less than B. Then we have f of B minus f of A divided by B minus A is equal to f prime of C, right? Does the mean value theorem apply here? Think about it. We're assuming that the function is differentiable on U, right? But if it's differentiable on U, that implies that it's continuous, because remember, differentiable implies continuous at each point. So we have differentiable, we have continuous. We can apply the mean value theorem on any subinterval. So what I'm thinking of here, if you want a picture of it, is you see U, and I guess I should say, I am thinking of, I guess I should say that, I'm not sure this is absolutely needed, but I really am thinking about it. U is an interval. In other words, it's a connected subset of R. I probably need that in order to not get hung up on something, but I'm not absolutely sure that's true. But anyway, that's my mental picture of U, is it's a connected subset. So it's something like this. It could have closed endpoints, but then, so here's U, that set of points, right? And the A and B, it gives you a little subinterval inside U. And on that subinterval, on the subinterval here, this is where we're applying the mean value theorem, okay? Like there. So, you guys tell me, what do I know? If f is increasing, what's that tell me? F of A is less than or equal to f of B, right? Which tells me what? That tells me that 0 is less than or equal to f of B minus f of A, right? And if you'll allow me to save myself some writing, what can we do If 0 is less than or equal to something, can I divide that inequality by a positive constant? Surely I can, right? So b minus a is constant. So I can divide this by b minus a, right? But that's equal to what? F prime of c by construction. And what do we know about f prime of c? Well, apparently now we know f prime of c is what? So f prime of c is apparently greater than or equal to 0. So this is the error in the statement of my theorem. I don't know for sure that the derivative is positive, right? If it's just increasing, because just increasing allows for the equality here, right? Now, if it was strictly increasing, then we could do what? We could replace that with a positive. All right, but anyway, so there we go. Greater than or equal to 0. And likewise, what's the difference? If f is decreasing, then we have f of a is, greater than or equal to f of b, which implies that 0 is greater than or equal to f of b minus f of a over b minus a, which is f prime of c. Therefore, f prime of c is less than or equal to 0. All right, great. That's it. So now this is the simple test. So here's our strategy, our algorithm, if you will. Classify, increase, decrease. All right, here's the algorithm. Number 1, find all critical numbers for f. Number 2, make sign chart for f, right? So if we've got let me just write it. I will give examples which make this clear. And then number 3 is just summarize the results. Right, so plus is increasing, minus is decreasing. Let's do a super boring one to get started. This one's really, really dumb. Wait a minute, did I ever move the camera? That would be really dumb. Oh, I'm going to start lecturing in shorts. Aye. All right, we good. So, this one, let me do 2 examples. They're just so dumb that they're hardly worth doing. Maybe I shouldn't even do these examples to start with because they're too dumb. F of x equals to e to the x. All right? So, if we calculate f prime of x, what do we got? E to the x. Is that equal to 0? Nope. Never, right? No such x. What's the critical number for the exponential? Nada. There's not one. So the sign chart for this is exceedingly boring. Here's df dx. And is derivative positive or negative? What is it? Yeah, positive. So the sign chart just looks like this. Very silly. Okay, so f increasing on everywhere. Example 2. What if we had f of x equal to, I don't know, I'll mix it up a bit here, 3 to the minus x. There you go. 3 to the minus x. What's the derivative of 3 to minus x? Yeah, negative natural log of 3 times 3 to the minus x. But you're right, there is a minus 1 from the derivative of the inside function. That's where that minus is coming from. Notice that this is in fact less than 0 for all x in the reals, right? So therefore f is decreasing on minus infinity to infinity. I could draw the sign chart, but it's just so silly. I mean, I'll do it. I'll call this f1, I'll call this f2. So here's the sign chart, df2, dx. It's just minus, 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 or minus, whatever. Yep.
So the derivative is negative, it's decreasing. Positive, it's increasing.
That's right. If the derivative's everywhere positive, it's increasing. And so this also will square with our previous pre-calculus intuition. See, because the graph of exponential, it looks like this, right? And the graph of 3 to the minus x, well, y equals 3 to the minus x is actually also 1 over 3 to the x, right? You could think of it that way. Anyway, the point is that the graph looks like this.
I got a question.
Yeah.
What if it's not everywhere decreasing or everywhere increasing?
Oh, well, that's like every other example I'll show you ever. Yeah, that's a good question. So that hasn't, I'd say that hasn't happened for us yet, but it's actually usually happened for us up to this point. We weren't talking about increasing or decreasing up to this point, right? All we did, the most we did, if you think back, is we found horizontal tangent lines, right? So if you think back, every time we found a horizontal tangent line, we were locating the point, which is a critical point. And technically speaking, if you look at those points, you would have gone from increasing to decreasing on one side or the other side of that horizontal tangent, right? Because you're coming up and going down, or you're going down and coming up. You're changing. So here's one. How about this? What if we look at f3 of x equals to x e to the x? This is always a nice example. Let's see if we can find any interesting critical numbers finally for this one. Right? So what do we got? df3 dx is what? Dx e to the x plus x ddx of e. I'm writing out the step here for a second. Most of you probably don't need that step written out at this point, but that's e to the x plus x e to the x. Now, the time has come when simplifying the answer actually really matters, because simplifying the answer will let you quickly and efficiently understand where this could be 0. So factor out e to the x. We've got 1 plus x e to the x, right? What are the critical numbers or number? Right, yeah, x equals minus 1. This is my only critical number, because the derivative is everywhere defined, right? So the only hope for us by Fermat's theorem is the place where derivatives are 0. That has to be the place where we have local extrema. Anyway, that also happens to be exactly the place where we can change from being increasing to decreasing, right? So I'm trying to be careful. There's a temptation, at least I had this temptation when I started studying calculus. And it's easy enough to do, to think about increasing or decreasing having meaning at a single point. In some sense that does. If you mean it to be, if you want to talk about increasing or decreasing at a point, we must be imagining all points near the point in that concept. See, because increasing or decreasing doesn't make sense at a single point. It has to be done over an interval. So if you want to talk about increasing or decreasing at a point, you must be talking about a neighborhood of the point to make the concept make sense. And it is true that if a function is increasing or decreasing at a point in the sense that it's increasing or decreasing at a neighborhood of the point, that the derivative must be respectively positive or negative at such a point, right? But be careful, technically speaking, increasing or decreasing at a single point doesn't quite make sense. Okay, anyway, so here, what's my critical number? -1. All right, now watch out for this. The big mistake students tend to make in this material is they plug numbers into the wrong formula, all right? So if we plug in 0, we should plug it into what? Into f or df dx. We should plug it into the derivative. So 0 is to the left of, wait a minute, 0 is to the right of -1, right? Goodness gracious. I'm not sure I can operate at this temperature. Well, not well anyway. So you guys tell me, positive or negative? Positive. Cool. And what if I plug in like -2? I get negative, right? And so what this tells me is f decreases on -∞ to -1, and f increases on -1 to infinity. And so I could actually hazard a graph. I could attempt a graph of this function. You see, it goes through 0 at 0. So it's increasing past -1, right? And so if it's increasing past -1, it's something like that, right? But it's decreasing. It's decreasing. It's decreasing to the left of -1. Question: where does it go to? So what I'm graphing right now is the function y equals x e to the x. Where does this have x-intercepts? Where does it cross the x-axis? How many places? Just what? Just the origin, right? Because it can only do there. Think about this formula. If I put this equal to 0, the only option this has to be 0 is when x is equal to 0. Exponential's never 0. This is only 0 at the origin, which means this graph can never cross back across the x-axis, right? So how can you have something that's always decreasing from -∞ to -1 and yet doesn't cross the x-axis? What's that mean? This has to be.
It starts close.
Mm-hmm. So it starts close to the x-axis, and it has to do one of these deals, right? So what does that make f of -1? Yeah, minus e to the -1, right? Also known as -1 over e, is a what? A local minimum, right? In fact, from the graph that we've just made, it's clear it's a global minimum. Is there a global maximum? I don't believe there is, right? Because the graph goes up and up, right? So sometimes a graph can have a global minimum, but not a global maximum, and vice versa. This is an instance of what's called the first derivative test. What does the first derivative test tell us? First derivative test says the following. Number 1, local extrema. Well, let me just kind of say it this way. You draw your sign chart. All right, so if this is C and it looks like this, plus, plus, minus, 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 all right, here's your df dx, right? For f prime of C, for C critical number, and f of C defined. In other words, I'm saying the context of the first derivative test is you're looking at a critical number where it's actually a critical point. All right, so like the value of the function at the critical point is defined. If the sign chart looks like that, and I'm ignoring what happens past here, all right? Like it goes on and on. We don't care what happens past this point or before this point, all right? If that makes sense to you, what I mean by this picture. What would that mean? That would mean that the graph looks like what at C? It's increasing and then it's decreasing, right? On the other hand, number 2, if your sign chart looked like minus is changing to plus as we're going from left to right for your derivative, then the picture looks something more like this, right? So what does the first derivative test tell you? If you draw the sign chart for the derivative and you look at a critical number, as you read in fact, a critical point, so f of c is defined, it's a point on the graph, well, then we know that that point is indeed a local min or max depending on the pattern. We know what it is depending on the pattern. So you guys, obviously case 1 is what? A local max, right? Local max. And over here, f of c is a what? Local minimum, right? There is a case 3 to the first derivative test. What would case 3 be? What's the other possibility at a critical point?
It's the same.
Right, yeah, exactly. So you either got minus, 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 and minus, minus, minus on the other side, or you've got pluses on both sides. Then, sorry, I'm going to use f prime if you guys don't mind. F of c, neither min nor max. Sorry, I can't really write down here, but I tried. I had this junior level electromagnetism professor. He could put his legs like Frogger, to the side, and then make almost like a right angle with his knees, and then he could write at the bottom of the board perfectly because he had this amazing squat. It was really something to behold. I do not have this. If I did that, I'd probably just stay like that. So again, this is an instance of the first derivative test. See, we go from minus to plus. That is, in fact, a local minimum. Does that make sense? Why is it important for it to be a critical point and not just a critical number? Let me remind you of the trouble which can come for, let's see here. Oh, that's interesting. I don't know what's on the board. By the way, it should go without saying, if you guys are working on homework and you've got a question about some problem you're stuck on, just ask in class, right? You can just jump in and ask. Especially at the start of class is a good time, but any time really. But I do mean to publish your list of homeworks that we're collecting. I just haven't done it yet. But you should be attempting the homework, right? Let's see here. So let's look at an example where we have critical numbers which are not critical points. Okay? How about this? Example, what am I on? 4? Yeah. Example 4. Maybe we're up against something like f of x equals to, I don't know, x squared divided by x squared minus, let's say, 9, just to keep things relatively simple. So what's the domain of this function? very good, yeah. So we've got trouble at minus 3 and 3, right? So what's df dx? Of course, those are vertical asymptotes, right? So df dx here would be 2x times x squared minus 9 minus 2x times x squared, I suppose, divided by x squared minus 9 squared by the quotient rule. Oh, hey, that's nice, because you see what happened there? Look at that. So we have this term here, and the term that comes from multiplying that and that, they're equal and opposite in sign, they cancel. Looks like we're just left with minus 18x over x squared. Maybe I made this too pretty. I'm sorry, guys. I mean, this is good. This is good. So there are 3 critical points here. What are they? I say critical points, I mean critical number. 3 critical numbers. We've got minus 3, 0, and 3. All right? So neither minus 3 nor 3 correspond to critical points, because minus 3 and 3 are not in the domain of the function. So if they're not in the domain of the function, then the first derivative test doesn't really apply there, is one way to think of it. So we've got minus 3, we've got 0, we've got 3. I guess I haven't really told you what we're doing in some sense, but just so you know, the goal today is to understand how the derivative tells us information about the graph of a function. Specifically, we're interested in finding where it's locally minimized or locally maximized, and we're also interested in finding the intervals of increase and decrease. We can do all of these things by differentiating the function, looking for where the derivative is either undefined or 0, making the sign chart I'm about to make, and applying the theorems. All right? So let's see here. We got what? Well, we got to make a sign chart. So this is easy enough to think about if you just want to think about it this way. The denominator is a quantity squared, right? Can this be negative? It cannot. Search your heart, right? It's positive. Although Jeremiah 17:9 says otherwise. It says that the heart is desperately wicked above all things. Who can know it? But the sign of this is governed completely by the numerator, right? So minus 18x is positive when x is negative. And it's negative when x is positive. So the sign chart we're looking at here looks like this. However, it would not be accurate to say that the first derivative test applies at minus 3 and 3, right? Why is neither minus 3 or 3 a local max or a local min? Because they're vertical asymptotes to the function, right? So that it's pre-calculus. It's not even calculus that we learn how to graph that. So here's the graph, like these, and put my vertical asymptotes in here like so. Here's your x equals minus 3. Here's the x equals to 3. You know, the basis for graphing is always the pre-calculus stuff, like college algebra. That we know that stuff. We still use it. For example, when is this got an x-intercept? Only for what? Only for the numerator being 0, which happens where? Just 0. Right, so that goes here. And then what? What can you tell me about 0 if you look at this? It's a what? A local max. So I guess technically speaking, best practice, I should really have also drawn, I'm sorry guys, whenever I'm graphing, I do try to draw both the df dx, but as well as the f itself. separate sign chart here. But it's funny, this one actually has the same, it has the same critical numbers, like the algebraic critical numbers and the differential critical numbers are the same in this one. However, the bottom is not squared, so I actually have to think through it. Like if I'm really, really positive, I've got positive. I flip signs here. I do not flip signs there, and I flip signs back over here again. I'm using the sign flip theorem from college algebra. If you guys know that, if you don't, let me write it out. So like if I look at the formula, y equals to x squared over x squared minus 9, I can rewrite that as x squared over x plus 3 times x minus 3. And the way this works is that if the factor is linear or if it's an odd power, you can change signs as you go across the critical number for that on the sign chart, on the sign chart for the thing. So x squared is always positive, or it's 0. It never switches from positive to negative. But the x plus 3 switches from negative to positive as you go across minus 3. And the x minus 3 switches from negative to positive as you go across 3, which is why we get this pattern here. Anyway, getting to the point, the graph looks like this. Now, how do I know that the horizontal asymptotes are 0? That's a good point. We know that the only 0 is at 0, so it can't cross the x-axis. That's one good argument. The other argument is just that if you take the limit as x goes to plus or minus infinity, oh, wait a minute. Uh-oh, oopsie. Oopsie, oopsie, I deceived myself. You guys tell me what happens here. We talked about this a little bit, I think. What happens if the limit is plus or minus infinity of x squared over x squared minus 9? Don't let me do that. Let me do that to you guys. How would we calculate that limit? There are various ways. One way I like is to divide the top and the bottom by x squared. And I'm just doing both limits at once because we can. So 1 over 1 minus 9 over x squared. What happens to 9 over x squared as x goes to either plus or minus infinity? It gets huge. 9 over something huge is 0, right? So this limit works out to 1 over 1 minus 0, also known as 1. This rational function has a horizontal asymptote of 1. Now, that's not something we could see with what? Did I use calculus to see that? Not yet. Not yet. So to see the horizontal asymptote, I need to fall back on my college algebra, right? There it is, or pre-calculus, whatever you want to call it. And there we go. Now that we've gone to the trouble of making this graph, we can answer other fun questions like, well, where's the function increasing? Let's see here. We've got it's increasing on minus infinity to minus 3. Yeah, union with minus 3 to, wait a minute. Oh, minus 3 to 0, right? And it's decreasing on, where was it? Basically minus 3 to 3, I think. We don't have to exclude 0, nothing, we don't have to exclude 0. Did I do that right? No, I didn't do that right. I'm sorry, just a second, guys.
Wouldn't it be decreasing from 0 to 3?
Yeah, I can't, yeah, thank you. It's not, I warned you guys, I can't think in this heat. Let's see here, 0 to 3. I didn't want to prove it to you, but I guess I have. 3 to infinity, yeah. because it's decreasing here and then also here. But to be fussy, at 3 it's not defined. Does this make sense? All right, let's see if I can find you guys another example. Let's see here. Now, I think this is enough for one day in terms of like concept-wise. We're going to do more examples, but there is one other thing that we haven't yet really, well, I guess there's 2 other things overall, but the one other big geometric idea we have to talk about is concavity. And it turns out that concavity is going to have to do with the second derivative. And once we learn that, then we can improve these graphs even a little bit better. So, but we'll probably do that tomorrow. So that's the other thing we have left to learn here. Past that, there's something called the closed set test we need to talk about. And then I apply it to word problems and such. But example 5. This one I have in my notes, which is nice. Oh, actually, I don't have this in my notes, but this one's actually kind of fun. F of x equals inverse tangent of, let's say, x plus 3. Let's see how this calculus works for this. What's the derivative? Right. To make this more fun, I'm going to take that x and upgrade it to an x squared. All right? Otherwise, it's too easy. If I do that, then what happens? We have to multiply by the derivative of x squared plus 3, which is what? We had to do that last time, but it just didn't produce. So what? 2x over 1 plus parentheses x squared plus 3 squared. So what are my critical numbers? Dang it. Someday I'm going to make it. I made it once, yeah. So what do you guys got for me? What's the critical number here, or numbers? 0? Yeah, I think you're right, 0. So this equals to 0 implies x equals to 0. That's, I think, the only critical number here. Notice that what's in the denominator is always, it's always positive, right? So the graph for df dx is kind of boring. It's just got 0 as its critical number, and I believe it's negative over here. It's positive over there. So we've got f increasing on 0 to infinity, and it's decreasing on minus infinity to 0. And what's that make f of 0? F of 0 equals f of 0 is inverse tangent of 3. This is a local what? It's a what? Local min? Very good. What's the limit as x goes to, say, plus or minus infinity of inverse tangent of x squared plus 3? Let's think through it. What's happening in this limit? We're, in either case, we're feeding the inverse tangent what? if you square a very large negative number, you get a very large positive number. Then you add 3, still positive, huge number, right? Either way you slice it, both of these limits concern looking at inverse tangent with a very, very large positive input, which gives us almost what? Almost pi over 2. Both of these limits go to pi over 2. So that is what we have to look forward to in terms of the large scale behavior of the graph. Y equals pi over 2 is a horizontal asymptote for this both ways. And so apparently the graph of this thing looks something kind of, sort of like whatever inverse tangent of 3 is. I have no idea. Funny. Well, I'm not sure what that is. I guess I could just get my calculator out. Oof. I'm in degree mode. That won't work, right? We need radians. Inverse tangent of 3 is about 1.25-ish. So 1.25, pi over 2 is approximately 1.57. 1.25 is like here-ish then. And so it's decreasing to there, and then it's increasing like over there. Yeah. An interesting question to follow up with this. So here's a question we might follow up. I'll probably forget, but it would be an interesting one to follow up. Where are the points of inflection for y equals inverse tangent of x squared plus 3? I mean, I can kind of tell you where they are graphically speaking. Not that we've defined these things carefully yet, but it's something like here and here. It's probably symmetric if I did it correctly. So if you can use your imagination, like close to here, it's kind of like a bowl facing upward, whereas over here it's like a bowl facing downward. So this function is concave down here, it's concave up in the middle, and it's concave down again. If we were to calculate the second derivative of this function, we could see that. Maybe tomorrow, if you guys will remind me. Example 6. Hopefully this one will be more exciting. So here we've got x to the 4th x to the 4th minus 12x squared minus 5. All right. So I don't think the zeros of this function are particularly nice. Like you could complete the square in x squared and figure out where this is 0. Would you guys want me to do that? Probably wouldn't hurt to see that. So before I even get into the calculus, where is this function 0? So we want more than that. We're trying to figure out not just where the function's 0, we want to figure out where the function's increasing, where it's decreasing. We'd like to find what it's called the turning points, right? The turning points are exactly the local mins and maxes. Here's how I'd find the zeros. That what I would do for this is I would look at this as f of x equals to x squared squared minus 12x squared minus 5. And then I would complete the square in x squared as such. X squared minus 6 quantity squared. See, if I have x squared minus 6 quantity squared, that gives me x to the 4th minus 12x squared, but then I've also added 36. So to be fair, I must subtract 36. So long story short, my damages are 41. And as such, this factors into x squared minus 6 plus root 41. It ain't pretty. And x squared minus 6 minus root 41. Now, the square root of 41 is larger than 6. So square root of 41 minus 6 is positive. Therefore, the first factor here is in fact prime. It's irreducible. That cannot be factored because it's x squared plus a positive number. On the other hand, the second one, annoyingly, it can be factored. And it factors as the following: x plus the square root of 6 minus the square root of 41, x minus the square root of 6 minus the square root of 41. So there, after some unpleasantness, what am I talking about? This is very pleasant. What could be more pleasant than doing college algebra that you haven't learned? Let's see here. So I'm just saying, if I put this on my college algebra final, I know I have sentenced 80% of my students to not getting credit for this question. I understand this, all right? Like, I'm not an idiot in regard to that. So the critical zeros here, we're going to have x equals to like plus or minus the square root of 6 minus the square root of 41. Oopsie. That was supposed to be the square root of 41 minus 6 is the way I should write that, as to not be a dummy. Indeed. Square root of 41 minus 6, I feel the same. So there you go. That's where this monstrous function crosses the x-axis. 2 places. If you want me to give you the digits, as my son would say, this is an off-brand number. It's not. All right, so this is about x equals to like plus or minus 0.635-ish. All right. We have not done a lick of calculus yet on this problem, but I hope you learned something. Right? That is one of our goals in here. Like, I sometimes hear this from students, like, I understand the calculus, I just get stuck on the algebra. No, the point here is for you to not get stuck on the algebra going forward. Like, one of your goals in this class is to master algebra. All right, so now that we've got that done, we know where it crosses the x-axis. Where is it increasing? Where is it decreasing? I sure hope the derivative is not so ugly. I'm pretty sure it's not. So differentiate, what do we get? So df dx is 4x cubed minus what? Minus 24x. Oh, look at this. This is so much easier, right? Factor out of 4x. And then what you got? You got yourself x squared minus 6. Oh, this is so much nicer. Look, so 4x times x plus root 6 times x minus root 6. But make no mistake here, you must know how to factor. If you can't factor, then you're in trouble here.